Industrial facilities, ranging from oil refineries to power plants, contain systems that transport liquids and gases from place to place. Some of these systems contain tubing or flexible hoses, but many of them contain pipes. Generally, pipe has thicker walls and is more rigid than tubing or flexible hoses. Because pipe is rigid, it is often difficult to bend. For this reason, piping systems usually require more fittings than comparable tubing or flexible hose systems. Numerous individual pipes make up the network of pipes in an industrial facility. This network is often called a piping system. In this part, we'll look at some common materials used to make pipes, and we'll examine some of their characteristics. The type of material used to make the pipe for a specific application depends on the chemical and physical properties of the gas or liquid that must be transported. These properties include the corrosiveness of the gas or liquid and the pressures and temperatures that the pipe is subjected to. While decisions on pipe materials are usually made by the engineers who design piping systems, anyone who works with pipes should be familiar with common pipe materials and their characteristics. Some of the most common piping used in industrial systems is made from metals such as carbon steel, stainless steel, and copper. One type of plastic piping called polyvinyl chloride, or PVC, is also widely used. Steel is metal that contains iron and carbon. The more carbon present, the stronger the steel. Carbon steel pipe is formed into different sizes while it is still red hot. Iron oxide forms on the exterior of the pipe as it cools, coating it black. Carbon steel pipe is extremely strong. For this reason, it is often used in high pressure and high temperature systems, such as hydraulic systems that push and lift heavy loads. Another characteristic of carbon steel is that it's less brittle than other materials, such as stainless steel, so it's able to absorb vibrations. Therefore, it is well suited for systems that generate significant vibrations, such as in vibrators, used to make anodes and aluminum manufacturing processes, lifts, and large gearboxes attached to motors or turbines. Because it is susceptible to corrosion, carbon steel is generally used with non-corrosive gases and liquids. Another material that's commonly used to make pipe is stainless steel, which is a steel alloy containing 12% chromium by weight. The relatively large amount of chromium contained in stainless steel gives it corrosion resistance, superior to carbon steel and other low alloy steels. Since stainless steel is stronger and stiffer than materials such as copper, it is well suited for use in high temperature and high pressure systems, such as hydraulic systems. Additionally, stainless steel can be easily sterilized by chemically treating the piping and then flushing it with water to remove the chemical residue. This prevents contamination and makes it a good choice for systems in pharmaceutical, dairy, and food processing plants. Stainless steel is also corrosion resistant, so it can be used to transport many corrosive liquids, such as acids and caustics. When copper ages, it becomes dark and dull and can be easily confused with other types of pipe. Polish a small area of the pipe to bring back the original color if you're unsure of its material. Copper pipes naturally resist rust that could contaminate the air. For this reason, they're often used in pneumatic systems such as conveyors, mills, pneumatic valves, and control valves. Though it works well in most environments and is strong enough to handle loads that might rupture a plastic pipe, copper pipe is best suited for use in systems in which temperature and pressures are not extreme. Copper is lighter and easier to install than stainless steel. However, it expands more than other materials, which can cause pipes to split and eventually burst. For this reason, it is not suitable for systems that handle extremely corrosive substances. Polyvinyl chloride, or PVC, is a common nonmetal used as a pipe material. PVC is a synthetic resin that is usually white or gray in color. When it's manufactured, PVC can have various chemical compounds added to increase its resistance to heat, light, or oxygen. PVC pipe is often used in the chemical industry, and it can transport liquids with temperatures up to 175 degrees Fahrenheit. Maintenance of piping systems often involves replacing worn or damaged pipes. In order to obtain the correct pipes for the job, maintenance personnel need to know how pipes are sized and marked for identification. That's what we'll look at in this part. Pipe sizes are generally given in terms of a dimension called nominal pipe size. For pipes from 1/8 of an inch to 12 inches, nominal pipe size is the approximate size of the distance from one inside edge of a pipe to the other inside edge, or the inside diameter. An approximate inside diameter is used to assign nominal pipe size because the actual inside diameter will vary based on the wall thickness of the pipe. Wall thickness is the distance between the inside edge of the pipe and the outside edge of the pipe. To determine a pipe's wall thickness, two measurements are needed: the inside diameter and the distance from one outside edge of the pipe to the other outside edge, or the outside diameter. To calculate the wall thickness of this pipe, we subtract the inside diameter from the outside diameter. Then divide that number by 2, because the pipe wall is on both sides of the pipe. Let's look at an example. The outside diameter of this pipe is 0.405 inches. The inside diameter is 0.269 inches. 0.405 minus 0.269 equals 0.136. 0.136 divided by 2 equals 0.068. 0.068 inches, then, is the wall thickness for this pipe. Once you have the inside diameter, the outside diameter, and the wall thickness of a pipe, you can use a pipe size chart to identify its nominal size. Using this pipe size chart, we can locate the nominal size for the pipe we measured in our example. Its outside diameter is 0.405. Its inside diameter is 0.269, and its wall thickness is 0.068. Though pressure is generally the concern of piping system designers, it is important for maintenance personnel to understand schedule numbers in order to identify the proper pipe for a specific job. The American National Standards Institute, an organization that publishes guidelines about pipe materials, sizes, and applications commonly used at many industrial facilities, has developed working pressure ratings for different types and sizes of pipe. The working pressure rating lets piping system designers, as well as maintenance personnel, know the amount of pressure a specific size and type of pipe can support. For example, this carbon steel pipe with a nominal pipe size of 1 1/4 of an inch has a pressure rating of 8,000 pounds. This means the pipe can be used safely in systems exposed to pressures of no more than 8,000 pounds per square inch. When you're joining pipe and fittings, be sure that they both have pressure ratings that meet or exceed the system specifications for pressure. So that the characteristics of metal pipes can be easily identified, several organizations have developed identification systems. Organizations that publish piping standards, such as the American National Standards Institute and the American Society of Mechanical Engineers, have their own identification systems. We're going to look at a commonly used identification system developed by the American Society of Testing and Materials, or ASTM. Under the ASTM system, pipes and fittings are printed or stamped with a series of letters and numbers called an identification number. Metal that contains iron or ferrous metal has an ASTM identification number beginning with the letter A. A non-ferrous metal identification number begins with the letter B. An ASTM identification number for PVC pipe typically begins with the letter D. A number, usually 3 digits, appears after the first letter. This number identifies the specific properties of the metal. For example, this pipe is printed with the ASTM identification number A106. This identification number indicates that the pipe is made from the ferrous metal carbon steel. The ASTM or other identification number for an individual pipe in a piping system is usually listed on piping specifications and project blueprints. Maintenance of piping systems can include performing routine inspections of pipes and pipe fittings for wear and damage. Following some basic guidelines for handling and storing pipes and pipe fittings can help lessen that wear and damage and protect against personal injury from heavy metal pipes. In this part, we'll look at some guidelines for all three operations: inspecting, handling, and storing pipes. Because a small leak or blockage in just one pipe can impact the operation of the whole system, routine inspections are an important part of maintaining any piping system. Inspections involve examining pipes and pipe fittings for wear and damage. One of the most common types of damage to pipes is corrosion. Corrosion is the dissolving or wearing away of metal. Corrosion can be either external or internal. External corrosion occurs when a condensation of moisture from the air or another source forms on the outside of a pipe. This makes the pipe appear to sweat. Over time, this moisture causes corrosion, which wears the metal away. Any dripping liquid can cause external corrosion as well. To stop continued external corrosion, the source of moisture causing the corrosion must be identified and eliminated. Internal corrosion results when oxygen in the air dissolves into the fluid carried by the pipe. Choosing a pipe material that doesn't interact with the environment, such as stainless steel, will help reduce both types of corrosion. Another common type of damage, dents, can diminish the strength and capacity of a pipe. Dents can be caused by mishandling pipes or improperly storing them. Replace dented pipe as soon as possible. During a pipe inspection, it is important to check pipes for signs of wear. Shiny spots on a pipe are common signs of wear. Providing additional support or protection to the pipe may be necessary to prevent additional wear. Finally, if a pipe is insulated or has a protective covering, these should be inspected as well. Look for soft spots, discoloration, or rust, which indicate that damage from moisture has affected the insulation. Worn or damaged insulation should be removed and replaced. Much of the wear and damage looked for during an inspection, such as dents, can be reduced if pipes are handled safely and properly. Handling pipes safely and properly can also help prevent injuries to personnel working with or around pipes. Safe and proper handling of pipes includes the following basic guidelines. Never drag pipes. Dragging a pipe can scratch or dent the outside surface, damage the ends, or contaminate sterilized pipe. Put end caps on pipes during handling and transport to guard against damage and contamination. Wear gloves to protect your hands from rough, sharp edges that could scrape and cut you. Only use vices equipped with special jaws for holding and protecting pipes. Conventional vice jaws can damage pipes. Be aware of the people and equipment around you when you're handling or transporting pipes. Put flags on the ends of long lengths of pipe so that you and others can easily see the ends and avoid damage or injury. Storing pipes safely and properly is important for many reasons. It can reduce wear and damage to pipes, make it easier for personnel to quickly identify different types and sizes of stored pipe, and help avoid injuries. Pipes are typically stored on pipe racks. These racks provide the support necessary to prevent bending, sagging, distortion, and scratching or marring of pipe surfaces. Be sure that pipes made from different materials are stored separately. For example, a number of aluminum pipes can be stored together, but they should not be stored with pipes made of copper. This makes pipe selection easier for maintenance personnel. Store pipes indoors when possible. Cover pipes stored outdoors with a tarpaulin or other suitable material. This will further guard against corrosion and contamination from sunlight and other environmental factors, such as moisture and changes in temperature. Many individual lengths of pipe comprise the network of pipes for a given process. The point at which a pipe is connected to another pipe or to a pipe fitting is called a joint. There are many different kinds of joints. In this part, we'll look at three of the most common: threaded joints, welded joints, and flanged joints. Threaded joints or screwed joints are made by screwing the outside threaded end of a pipe into the inside threaded end of a pipe fitting. Threaded joints have a specified engagement depth. The engagement depth is the distance that the pipe must be turned into the fitting. The engagement depth requirement must be reached for the joint to be properly threaded. As pipe size increases, engagement depth also increases. Threaded joints are typically used for smaller pipe sizes, which carry lower pressures. Threaded joints are relatively easy to make and they don't require welding. This is an advantage in places where fire hazards exist. On the other hand, threaded joints tend to weaken the pipe wall because the pipe's wall thickness is reduced at the troughs of the threads. Threaded joints are also subject to leaks if they are improperly tightened or sealed. There are two types of welded pipe joints, socket weld and butt weld. In a socket weld joint, a pipe is inserted into the socket of a fitting that has an opening larger than the pipe's outside diameter. The edges of the socket are then welded around the outside of the pipe. To create a butt weld joint, the beveled end of a fitting is lined up with a pipe. Then the edges of the joint are welded around the outside of the pipe. A flange is a flat metal plate attached to the end of a pipe. It can be bolted to a flange on the end of another pipe to form a flanged joint. Flange joints are leak-proof joints that are easily taken apart for inspection or maintenance. The many individual pipes in a piping system can be connected to each other using various types of joints. The devices used to make these connections are called pipe fittings. In this part, we'll look at some common fittings and examine their functions. Pipe fittings are generally the same nominal pipe size and material as the pipes to which they're connected. Fittings are typically designed to perform one of 5 functions. They can connect pipes and components. They can extend the length of a straight pipe run. They can change the direction of a pipe run. They provide branch connections. And they can close off the end of a pipe run. Let's see how various types of fittings perform these functions. We'll start with fittings that connect pipes and components. This fitting is called a coupling. Couplings can be used to connect components in a piping system, such as 2 pieces of pipe. Couplings typically have inside threads on both ends that can connect to 2 components that have outside threads. Couplings can be threaded or welded to pipes. Welded fittings have no threads. Because a bushing has one end larger than the other, it can be used to connect a pipe of one size to a pipe of a different size. Threaded bushings generally have outside threads on one end and inside threads on the other end. Bushings can also be welded. A union is another threaded or welded connection for components in a piping system. Unions are often used to connect components that can't be turned and screwed together, such as 2 pieces of pipe that have been bracketed to a wall. This is a threaded union. It has 3 parts, a nut and 2 end pieces with inside threads. To make a connection with a threaded union, the 2 pipes to be joined are screwed into the 2 end pieces of the union. Then the nut is tightened to draw the 2 pipes together. Pipe fittings such as this one, called a nipple, can also be used to extend the length of a straight pipe run. Nipples have outside threads on each end, so a fitting with inside threads, such as a coupling, must be used to connect a nipple to a pipe. Nipples come in a range of sizes and are classified according to nominal pipe size. Nipples are actually pieces of pipe that are less than 12 inches long. Nipples come in a variety of sizes. Some commonly used nipples include this very short nipple called a close nipple, this longer nipple called a shoulder nipple, and this short nipple. Now let's look at some fittings that change the direction of a pipe run. This elbow is one example. Elbows come in a range of angles, but the most common are 45 degrees and 90 degrees. There are 2 primary types of elbows, long radius, and short radius. These are 90-degree long and short radius elbows. This street elbow is unique because it has outside threads on one end and inside threads on the other end. Threaded elbows generally have inside threads on both ends. Elbows can also be welded to pipes. Another function of pipe fittings is to provide branch connections. Pipe fittings that provide branch connections are used to divide the flow of fluid in a pipe run into two or more branches. One of the most commonly used branch connection fittings is called a T. T's are used to join a main pipe run to a branch pipe run at a 90-degree angle. T's come in a range of sizes and designs, and they can be threaded or welded to pipes. Crosses are another type of branch connection fitting. The two branch outlets form the shape of a cross. Like T's, crosses can be threaded or welded to pipes, and they come in many sizes and designs. T's come in a variety of designs. One common design is the straight run, reduced branch T. It is used to connect two same-size pipes in a straight pipe run to a branch. The built-in reducer at the branch connection reduces the flow of fluid from the run into the branch. Another common T design is this reduced run T. The reduced run T connects a pipe run to a branch. It also has a built-in reducer to reduce the flow of fluid from one of the run connections. In addition to connecting a pipe run to a branch, this reduced T has built-in reducers at the branch outlet and at one of the run outlets. Crosses are another type of branch connection fitting. The two branch outlets form the shape of a cross. Like T's, crosses can be threaded or welded to pipes, and they come in many sizes and designs. Caps and plugs serve another function of pipe fittings, which is closing off the end of a pipe run. Caps and plugs, such as these, are available in a variety of sizes and shapes. Threaded caps have inside threads. They're used to close off the ends of components that have outside threads. Threaded plugs are similar to caps, except that they have outside threads. Caps and plugs can also be welded to the ends of pipes. Pipes come in a wide range of sizes, and they can be made from many different materials. Joints and fittings can be used to connect individual pipes to form a larger piping system. Before a pipe can be installed, the length of pipe needed between two fittings must be calculated. In this part, we'll look at three methods for calculating the length of pipe that's needed. To calculate the length of pipe needed between two fittings, there are three basic methods: the center-to-center method, the face-to-face method, and the shoulder-to-shoulder method. Let's look at an example to see how to calculate the length of pipe using the center-to-center method. First, measure the distance from the center of one fitting to the center of the other. Next, measure the distance from the center of each fitting to the face of each fitting, like this. Now subtract these two measurements from the first measurement. Next, measure the engagement depth of each fitting, or locate them on an engagement depth chart. The engagement depth is the distance that a length of pipe is turned or threaded into a fitting. Then add the two engagement depth measurements to the result of your subtraction. This is the length of pipe that is needed between these two fittings. You can now measure and mark the pipe for cutting. Use a felt tip pen to mark PVC pipes or a pencil for metal pipes. Calculating the correct length of pipe with the face-to-face method generally consists of two steps. Let's look at an example. First, measure the distance from the face of one fitting to the face of the other fitting. Add the engagement depth of each fitting to the face-to-face distance measurement from step 1. And this is the length of pipe needed between these two fittings. You can now measure and mark the pipe for cutting. The final method we'll look at for calculating the correct length of pipe is the shoulder-to-shoulder method. This method has only one step. Take a look at this example. This is the shoulder of a fitting. Measure the distance from the shoulder of one fitting to the shoulder of the other fitting. And that's the length of pipe needed to fit between these two fittings. You can now measure and mark the pipe for cutting. A variety of sizes and types of individual pipes can be connected with different joints and fittings to form a larger piping system. Before you can install a pipe, the length of pipe that you need must be determined and the pipe must be cut to size. In this part, we'll look at some common pipe cutting tools and see how they operate. Generally, pipes are cut with pipe cutters or saws. The particular cutting tool you use will depend on the size and type of pipe to be cut. Be sure to check the manufacturer's manual to make sure you select the correct cutting tool. First, let's look at pipe cutters. Pipe cutters are devices with rotating cutting wheels that circle around a pipe to cut it. Cuts can be made quickly, smoothly, and accurately with pipe cutters. Pipe cutters rotate around the entire pipe, so they can only be used in areas with enough space to accommodate the complete rotation. To cut pipe with a pipe cutter, first place the cutter over the pipe and align the cutting wheel with the mark where the pipe is to be cut. Next, tighten the cutting wheel using the handle. Then, rotate the cutter around the pipe, tightening the handle gradually. This causes the cutting wheel to cut into the pipe. Continue rotating the cutter and tightening the handle until the pipe is completely cut through. Reducers are often built into fittings that change the direction of straight pipe runs and fittings that provide branch connections. But they can be separate fittings as well. Like most other pipe fittings, reducers can be threaded or welded to pipes. A reducer allows a larger pipe to be connected to a smaller pipe. This is often done to increase pressure in a piping system or to reduce the volume of fluid through the system. In addition to pipe cutters, hacksaws and bandsaws are commonly used to cut metal and plastic pipe. We'll look at both of these tools, beginning with the hacksaw. Hacksaws have hardened tempered steel blades. A pitch of 1/18, for example, means that the blade is 18 teeth per inch. The most common blades used for cutting pipe have 14, 18, 24, or 32 teeth per inch. Thin-walled pipe generally requires a blade with smaller teeth or a higher pitch. Be sure to select the blade with the correct manufacturer-recommended pitch for the pipe you are cutting. Guide blocks are often used to hold pipe steady while it is being cut with a hacksaw. This ensures a straight cut. Cutting is done on the forward motion of the blade, with two teeth of the blade in contact with the pipe at all times. The hacksaw blade should be kept as perpendicular to the pipe as possible, or else the cut will be uneven. Bandsaws cut much faster and cleaner than hacksaws or pipe cutters. To make a good clean cut with a bandsaw, very little pressure is needed. Be sure to select the correct blade for the size and type of pipe that you're cutting. Generally, a fine-toothed blade is used with soft materials and when a smoother finish is desired. A blade with a pitch of 1/32 or 32 teeth per inch is a good choice for a fine-toothed blade. Thicker materials are best cut with a coarse tooth blade, such as a blade with a pitch of 1/14 or 14 teeth per inch. No matter which tool is used, cutting pipe can leave burrs and ridges on the inside or outside of the pipe. Burrs are bits of jagged pipe. A ridge is a lip or shoulder that's left on the end of the pipe. Burrs and ridges can restrict the flow of liquid or gas through a pipe. They can also prevent pipes from becoming properly connected to pipe fittings. Pipe reamers, half-round files, and rat-tail files can all be used to remove internal burrs and ridges. A pipe reamer, such as this one, has a cone-shaped file that can be inserted into a pipe. This is a half-round file. Its file is a circular segmental section that is tapered in thickness and in width. A rat-tail file, such as this one, has a tapered body that comes to a very small point at the end. Insert the reamer or file into the pipe enough to exert a slight pressure without damaging the pipe wall. And rotate the reamer or file inside the pipe until the pipe surface is smooth and free from burrs and ridges. A rat tail file should be used as a last resort when a reamer or a half-round file will not fit inside the pipe. Rat tail files can leave marks on the inside wall of the pipe, which makes the pipe wall thin and susceptible to early failure. A flat file can be used to remove external burrs and ridges. Move the file around the pipe in an arc-like motion. Using a flat motion can flatten the pipe. Minor external burrs and ridges can be rubbed away with emery cloth. After all burrs and ridges have been removed, wipe the pipe clean, inside and out, with a rag. Shavings left inside the pipe can contaminate the fluid in the system and clog filters or other components in a piping system. A variety of sizes and types of individual pipes can be connected by joints and fittings to form a larger piping system. Before the pipe can be installed, the length of the pipe that you need must be determined. The pipe must be cut to size, and the pipe must be threaded. In this part, we'll see how to use a pipe die to cut threads on a pipe. The threads of a pipe are created with a pipe die. A pipe die is a tool that has teeth that cut into the outside walls of the pipe to form threads. There are three important considerations to keep in mind when you use a pipe die to thread a pipe. They are the size of the die, the number of threads per inch, and the length of the threads. The size of the pipe die should match the nominal size of the pipe being threaded. For example, this pipe die has a nominal pipe size of 3/8 of an inch. It can be used to create threads on pipes with a 3/8 of an inch nominal pipe size. The pipe die you use must also cut the correct number of threads per inch, or else the pipe threads will not match the threads on the fitting. You can use a thread gauge, such as this one, to calculate the number of threads per inch on an existing pipe or fitting. The final consideration when you're threading a pipe is the length of the threads. Threads that are cut too short will be weak at the joint and will leak. Threads that are cut too long will make creating a joint difficult, which may also cause a leak. Pipes can be threaded in different ways. Electric pipe threading machines may be used, but we'll use a hand-operated pipe die as an example. There are a few basic steps to hand threading a pipe with a pipe die. First, you should secure the pipe in a pipe vise and apply cutting oil to the end of the pipe. This provides lubrication and reduces the heat that's generated when the die cuts into the pipe. Next, press the die against the end of the pipe and turn it clockwise with a ratchet handle. Once the teeth of the die grab the pipe, you can continue turning the die without having to press it against the pipe. It may be necessary to apply additional cutting oil after a few turns as well. The pipe is fully threaded when 2 or 3 threads appear on the outside of the die. At this point, you can back the die off the pipe by reversing this knob on the ratchet. It may be necessary to move the die back and forth on the pipe as it is being removed. This removes some of the metal chips and ensures that the threads are not damaged. Now, remove the remaining chips and shavings from the pipe with a wire brush and apply a thread lubricant or a thread sealing compound to the pipe to prepare it for connection to a fitting.